First, my congratulations to Mike and Eric. And while preparing this talk, memory and computing with full memory, of course, I have to talk about memories I have about you two guys. And I know Eric the longest. And actually, from my memory, the first time I met you was in, do you know? Let's see if it is the same.
You tell me. Okay.
It was Structures 1990, which happened to be my first conference, and it was in Barcelona, of all places, so that was fantastic. I really enjoyed it. Actually, Avi was there as well. And Lance was there, and Steve was there. Many people were there. And Eric had a paper. Do you remember?
No.
The title of the paper? See, that happens with computing with too full memory, right? You lose stuff. It was called Width-Bounded Reducibility in Binary Search over Complexity Classes. And the main result was a characterization of p to the np log. It's coming back now, I think, a little bit. So Structures in Barcelona was a lot of fun. They gave you this nice bottle, which I still have. I made a picture, which really is a good Rioja, they said. I remember that the people organizing this conference were drinking these bottles long after the thing was passed. It was about reductions, completeness, and complexity classes. It was called Structure in Complexity. It was the time of interactive proofs before the PCP theorem, which was great. And also, sorry Lance, I found a paper, an errata of Fortnau, Rompel, Sipser on parallel repetition, which was all the way in the back of the proceedings.
So Ron Raz found a simple proof.
Yes, and then Ron Raz, indeed, a little bit later, fixed that part. I asked Peter van Em de Boas to come up with some pictures, and here are two of Eric, one from before Barcelona and one after. Yeah. Spot the differences. I guess this one was in Amsterdam, and this one was the second Structures ever. We also I have fond memories of us being in Maine, where Steve Fenner on the left here organized a variant of DAGSTOOL, which is a conference place in Europe, but then in Maine, where we had lobster and all kinds of fun. Here's some more of these pictures. Eric sitting there in the back. See Fred Green. Luc Lompré, I see. So lots of old people for some of the oldies here. Lots of fun. So memories of Mike. So I know Mike not that well, but we met, and do you remember the first time we met? Very good. Indeed, it was Barbados in '96, which for some of you who go to Barbados, actually Eric was there as well, I remember that. It looked like that then, and I think here is now the place where they changed it and we have the lectures, but then we had the lectures inside. And I don't have many pictures of people from that time. But I do have the pictures of these two dogs that probably are no more, but I thought they were cute and nice and friendly. Of course, at the back of Barbados, you can swim and snorkel and have fun, although that has changed also drastically in the last few years.
Really?
Yes?
I was there 5 years ago. No, 2 years.
Okay, yeah. Well, there is a lot of change, and not to mention the coral reef, which is diminishing because of global warming. So this workshop I went to was on the PCP theorem. Sanjeev Arora gave the talks, and I did talk to Mike about distributed computing. Do you remember that? Wow. Fantastic, because at that time I had ventured a little bit into distributed computing and I was interested in weight-free renaming, and Mike had a very nice paper solving the problem I was looking at, or actually he had already solved it before I started looking at it. And this also showed that this field of distributed computing was actually kind of very interesting, and there was a nice connection between topology and Brouwer's fixed point theorem to solve a particular weight-free solution for an algorithm, or at least to prove a lower bound on that. So that was very nice. And then in 2001, I have some pictures because that was the first time I actually bought a digital camera. And so there's some nice pictures of people who are around here. You see Mario here, and Ilan Newman was around. Also got a picture of Mike talking to Howard Barnum. Probably talking about quantum query complexity and semi-definite programming. Must have been that. These are my kids, and for Lance, Annie is there. And where's Mario? Mike is there. That's me. Let's go on. So we were doing some nice things in the garden. Eric probably remembers. And what were we looking for?
Well, they're strawberries.
Strawberries, yeah.
Yes.
There were strawberries. Very good. So you remember the strawberries. The paper is still there, the strawberry not. So it was a general happy time, and I enjoyed it a lot. So, with our heads full of memories, now getting back to my talk, can you do computation with a full memory? In the following sense, consider now the following scenario where I want to do a computation and I have a certain amount of free space available, and I need more space. So one thing you could do is go to the store and plug in an extra hard drive and happily continue, but it so happens that you have a hard drive, but it is full with pictures and memories, like these. And of course, you don't want to erase them, you don't want to get rid of them, you want to keep them. So the question is, can you do this computation, which needs more space than you have available? Can you do that by adding on a hard drive, but with the caveat that after the computation is done, this hard drive should be in its original state, should be having still all these pictures there. So can this extra space be of any help? So a little bit more formally, in a Turing machine model, we have our Turing machine. We start with our free space, and we start with an auxiliary tape, and we have our input, which is n bits. And then during the computation, anything may happen to this additional hard drive, to this additional auxiliary space, but at the end of the computation, the original content should be there. And moreover, this should work for any initial starting state. So we're focusing here on where the free space is only order log n bits, so a log space variant thereof, and we call this catalytic log space. So we have log n clean space, and we have this additional auxiliary tape, maybe polynomial in size. And so the question is, does this help? Does this extra tape help? And a first attempt that you might do is the following. Well, first I try to compress the stuff that's on my hard drive, then use the additional space that is freed up, and after I've done my computation, uncompress and give back the hard drive. Well, that doesn't work if the stuff that's on your hard drive is random and is incompressible. So this idea doesn't work. So what about the following idea? I just make my program reversible. So I make it reversible, which can be done with not too much overhead. I use the extra space as normal space. I copy the answer when I'm done, and I reverse my computation. Now that sounds also nice, but that doesn't work either, because a reversible computation wants your space to start out clean. And in this case, it isn't clean most of the time, so this doesn't work either. So it seems that this additional space is really useless, right? It's sitting there, it's this big random string, and this information has to be maintained throughout the whole computation. You cannot get rid of it, because it has to be there in the end. So let's try to prove it's useless. That's at least what we set out to do, and then we were in for some trouble. Because the following thing can happen. So here I have my computation, and I'll suppose that for a certain setting of my hard drive, for a certain setting of this auxiliary tape, it happens to be all zeros, right? It could be that it's all zeros. So I could check and see, oh, it's all zeros. And in that case, I just run a counter for 2 to the polynomially many steps, and then I set out to do my computation that I wanted to do anyhow. So what this complication says is that sometimes a catalytic machine can run for a very long time and still be catalytic, right? But it only runs for polynomial time, in this case, when I have this initial, the auxiliary tape be all zeros. So they can run for a very long time. So the first result I want to sketch to you is to show that catalytic space is somewhat limited, so it doesn't give you full space, but it sits in ZPP. And so here's a useful way of seeing that. So define for any catalytic machine M this the contents of the tape and transition function and everything on input X and auxiliary space W. So it started out with a W at time t. So that's this information. And now, so that's the local tape plus the catalytic tape plus the state of M. So that's a big register that contains lots of stuff. So now a lemma that is fairly easy to prove says the following. Suppose that I have a machine M and an input X, and I have two different catalytic instantiations of my tape. And then for all time t and t prime, it can never happen that these two IDs are the same. So in pictures, if I start out my catalytic computation on X and W, and I follow this path, and I would start it out on another W prime, then these paths should never cross. They should never combine. For if they would combine, so if these two paths would combine, then from this point on, because my computation is deterministic, it would end up in some W tilde, and this W tilde has to be different from W or from W prime. And the catalytic requirement said that at the end of your computation, it should give you back W, and in one of these two cases, or maybe in both, it's wrong. So these paths cannot cross. So now here's the proof of why catalytic space is in ZPP. So let T of XW define the number of steps that M makes on X and W. So we can easily count that there are 2 to the length of W times polynomially many different ideas possible in total, right? That's all the possible settings of my auxiliary tape plus the settings of my local free space. So this is the total number of possible IDs you can see. And now using the lemma, if I sum up over all T's, over all W, this total number of steps, then it is to be bounded by 2 to the W times n to the C, right? Because I cannot have double counting there. So now moving over the 2 to the W to the other side, then you see that you get that the expected running time, or the expected number of steps over a W chosen at random, is polynomial. And now that gives you a polynomial time randomized algorithm, because when you want to simulate this M, you instantiate its auxiliary tape with random bits, and you run it, and if it stops, well, then you know what the answer is, and if it doesn't stop, well, then you try again, and the expected number of steps that you have to take is polynomial. So you are a ZPP algorithm. So this shows that with catalytic space, you don't boost up all the way to P space. You're sort of limited to ZPP, and probably P if you believe in this de-randomization hypothesis. So then we set out to think of, well, so we have that log space obviously is a subclass of catalytic space, because you don't have to use your catalytic tape. So we were setting out maybe catalytic log space is a little bit more powerful than log space. Or is it equal? We didn't know. And so we set out. And then in the back of our minds was always, or at least in my mind, was this example that I guess you get if you apply for a job at Google and you have to solve one of these programming quizzes. So suppose that you have two variables, x and y, that contain an input t of x and t of y, and you want to swap them, right? You want that at the end of the day, t of x is in variable y, and t of y is in variable x. Now, of course, you can easily do that if you have a third register z available, right? Because you put first x into z, you copy it there, then you put y into x, and then you put z into y. And so the question that they ask you, perhaps at Google, is, can you do it with just 2? Can you do it without this extra one? And the answer is yes, and you probably have seen this. And here's how you do it. So first, you put into register x the difference of y and x. And I'm using the notation here, this double slashes here, to notate what is now in the content of variable x. So when you do this, when you execute this command, then ty minus tx sits in x. Now the second thing you do is you set y equal to y minus x. So that means that y is ty, and you subtract, well, what is in x now, which is ty minus tx. So that is tx, right, if it sort of cancels here. And thirdly, you perform the opposite. You set x equal to y plus x. And since y contains t of x, and x still contains t of y minus t of x, you now add t of x to this content, and you get t of y. So with these 3 simple instructions, you have swapped x and y without using an extra one. And this idea, actually, there's more truth to it, at least in applying it to our catalytic computation, than we thought at the beginning. And here's what we can show. We can show that actually catalytic space is quite more powerful, or so it seems, than log space, because it contains all of NL, and it contains even more. It contains this class TC1, which is polynomial size log depth circuits with majority gates. But I'm focusing here on the NL part, which is easier to prove, and I can give you full proof of that. I have to say, though, that this result is a little bit more complicated than what I'm presenting here. But since people believe that NL is not equal to log space, non-deterministic log space is more powerful, this also shows that those people also believe that catalytic space is more powerful than log space. And in particular, I will show that you can compute the determinant in catalytic log space. So think of that, I have log space available. We don't know how to compute the determinant with just log space at our disposal, but now when I give you this additional hard drive, you can compute the determinant of your matrix, giving back the hard drive at the end of the computation. So in order to do that, we follow up on this idea of switching these 2 variables, and we come up with something that we call transparent programs, and they're the following. Imagine that you have a bunch of registers, m plus 1 of them, and they contain elements from a particular ring, and we want to compute a function from n values of this ring to a value of the ring itself. So here we have our input. So we have our n registers, n plus 1 registers, and we have our input x1 up to xn. And we want to compute that f. And now the instructions that you get to play around with.
Little m is like log n?
No, it will actually be, in our example, it will be polynomial. But here, here I can just do it for any m and n. And the instructions that you get available are the following. So you can change the register Ri by adding or subtracting to it the product of Rj times Rk. And here all operations are done in the ring. Or you can choose to add or subtract an input register or a product of an input to one of the other registers. So these kinds of instructions are allowed. You can use them in your transparent program. And the goal at the end of the day is to have the value of f of x be computed somehow in R0 in the following sense, that f of x is added to the original value that is in R0. And mind you, we don't require any settings of these registers, so they can be set in any way with elements from the ring, and there will be. And still, at the end of the day, you have to accomplish that task. Note that also these programs, when we perform them, these transparency programs, they are reversible, because if I add something, if I had an instruction of the following form, then just subtracting it would be the inverse of that, right? It would undo what you did before. So these programs are very naturally a reversible set of programs, or they can be made very, very naturally reversible. So now, how is this transparent programming going to help you in our catalytic quest? And here's how. So again, we have our input here in our clean space and our filled auxiliary catalytic tape. And what we do now first is we divide our catalytic tape into m+1 registers that we now think of having are the contents of these m+1 registers, and we assume that the settings of this tape now code for elements of our ring. So we just imagine that the catalytic tape looks like that. We haven't touched it, we haven't changed it. This is how we set up things. And now imagine that the entries of these registers are small. If they're not, there's things we can play around with. For the moment, think of them as small. And we copy the value of R0, so the value of this part of the catalytic tape, into our clean memory. We can do that. And now we run a transparent program for f. Suppose we had one that is in polynomial, has polynomial size, then we can certainly run it. And we use our clean space in addition to figure out which instruction has to be carried out next. And we just update the registers on the hard disk that we have to put back. But for the moment, we can change it. So at the end of the day, we have computed the value f of x into register R0, and all these other registers may be screwed up completely. Right, the transparent program doesn't have any guarantees on those. But now, when we're at this spot in time, we can actually extract f of x by copying the value of this register into our clean memory and XORing it, or adding it, which gets rid of the t0, or actually subtract t0 from the value here, which gives us f of x, and has this catalytic space the way it was at the end of the program. And now we run the inverse of our program, undoing all the stuff that we did. So we have computed f of x, and we have returned the whole catalytic space to its original settings. And that's precisely what we wanted to do. So the question of what can you do with catalytic space comes down to what can you do with these transparent programs, or at least if you can do something nice with these transparent programs, you can do something nice with the catalytic space. And this is what we started to explore, and there was actually a very nice paper already around, also from the time I was talking about when I met Eric and Mike. And this is a paper by Ben Orr and Cleave, and you can formulate it in the following sense. It says that if you have arithmetic formulas of polynomial size and logarithmic depth, and we have multiplication of Fedin, and we have a plus that's unbounded, so you have these gates at your disposal, and it sort of is log depth and it's polynomial size, and here are my inputs, then you can compute this formula with polynomial size transparent programs. That's of course not how they phrased it, but that's what you can extract out of there. And here's the proof. It sort of goes by induction on the depth of my formula. And as induction hypothesis, I use the following. I say I have a program up to depth d minus 1 that computes in Ri. It can add to the value Ri Rj times the f that I have computed up to that length, right? So, for example, I'm at this point in time, and I call the value that is at this point in the circuit, I call that f. And I also have a program P2 that does the same thing for a value g. Then, and we're going to show that works, then I can actually have one more depth. And if I want to compute f plus g, so if my gate that I wanted to compute was a plus gate, then I can show you how a transparent program looks like that puts now f plus g into Rj, or that puts the product of f times g into Ri. So let's look at the plus first, because that's a little bit easier. That's actually straightforward. So the base case for both plus and times is easy, because I'm only dealing with my input registers, and clearly I can have the following program that puts in rj the value of rj times plus rj times my input variable xk. So the base case is trivially covered. It's really only interested to go from here to here. So how does a program for f plus g look like? So my induction hypothesis tells me I have a program, and I put here superscript I and j so that it works with registers I and j, that puts rj times f plus ri in ri. So I have a program. My induction hypothesis gives me a program for that. So let's run it. And so in our register ri, we have ti, which was the original value, plus tj times the value of f. Now I also run, after I've done that, the program that does the same thing for ri, but then g. And so when I run that, then I see that I have added an other times tj times g into my register ri. Right? Running the first program and then the second has the result that this is now the content of ri, which is precisely what I wanted. Right? This is ti times tj times f of g. And that's exactly what I needed to show here. And note that I can keep adding stuff, and I just have to run more programs. So I can trivially add polynomially many stuff. So my unbounded plus gate is fine. Now actually the times gate is slightly more complicated, and here something almost magical seems to happen. It just works.
Barrington magic.
What?
Barrington magic.
Yes, Barrington magic, or in this case maybe Benor-Cleave magic. Yes, and yes, absolutely. Okay, so I do the following. I first run for a different register now, rk. I run a program that puts into rk rj times f. So now I have in my register rk tk plus tj times f. Then I run my program for g, but now I run it for ri and rk, and the rk that I just changed over here. So when I do that, then the contents in ri are going to be this value, ti plus tk plus tj times f times g, which is this value when you work it out, ti plus tk times g plus tj times f times g, and it's almost right, except for this term. Right? This is too much. You've added too much to ri. So we're going to fix that. We're going to get rid of that by the following magical program. We first undo the program we did here. So we do p inverse of p1, exactly the way we did it, which actually puts back rk to its original value. And then we run the inverse of program 2. And when you do that, it takes away exactly this tk times g value. And it has in its register exactly what you wanted. Right, so putting these 4 instructions together actually performed exactly this times thing. It's very, very nice. And this concludes actually the proof. Note that every layer you add, so every increase of depth, requires your program to blow up by a factor of 4. So it's 4 to the d instructions of depth d. So we can cover log, but not more. And note also that actually only 3 registers were used and not more. So you can, I sketched it in all generality, but really only needed 3, ri, rj, and rk. And also note that I only use, if you really analyze it, skew instructions, which are instructions that have at the second place either an input variable or a constant. So it's a very limited set of instructions here. So how can we use that? Well, very trivially, here is an arithmetic circuit for arithmetic formula for computing the matrix, iterated matrix multiplication. Right? It's just stupid products all the time, and my matrix here at the bottom. And this computes matrix, iterated matrix multiplication, and hence by the previous result I have a transparent program for doing this. All right, and since computing the determinant, computing the determinant can be computed from doing iterated matrix multiplication, I have that NL is inside of catalytic log space.
Every unit is a matrix entry, or it's
Yes.
a matrix? But
Yes.
then if it's a matrix entry, then it's not product, it's inner product. Which is okay, would be okay. I mean, I don't know why you put only products. If the matrix entries are the inputs, then you need.
No, actually, sorry. Here I use the ring is the ring of matrices.
It's the matrices, okay.
And,
So
my product is the product of matrices
Okay.
in that ring.
okay, but you could also do, if you wanted, the matrix product with where the inputs are the
Unbounded
entries, right?
fan.
You mean just to compute inner products?
Well,
Row by
just
column.
the inner products are unbounded fan in 4 plus, and so you can have your inputs be the entries.
Sure.
Okay.
Yeah, actually, I was thinking that you were going to point out that these entries now, the ring elements are not. I cannot copy them in log space anymore, so I have to revert to entries there. But somehow presenting this as a result, it's slicker to do it this way. But you're absolutely right. You have to revert to the entries in the end. Yes.
The transparent programs can do elementary row operations, right? So you can just do Gauss-Jordan elimination or something.
Okay.
Right?
Probably, but and what?
Well, it's another way to express that you can do these matrix operations.
Okay. Yeah.
So, regarding the result that you had before about the bounded multiplication, bounded addition, is there a reason why this does not extend to semi-unbounded log CFL, semi-unbounded AC1?
No, I think we get the log CFL case. So we get actually. Let me go to the next slide, and then that answers your question, at least hopefully. So we get all the way up to TC1. So note, because of these two nodes, we only used 3 registers here, and we only used skew instructions. And when you let go of that, because this transparent program formalism allows you to do that, you can actually get more. But with a little bit more complicated methods, you can get actually all of TC1. But that's as far as we know where it stops. We have no clue whether you can do more than that or not. So, taking stock. So this catalytic log space is very useful, and we have this catalytic programming technique. And these transparent programs, they are reversible, and sort of the obligatory structures line that you get here is that you have this series of inclusions, and we don't know whether any of these are strict or not, right? For all we know, it could be that L is equal to ZPP, although we don't believe that, but we don't know where it sits, where catalytic log space sits. It could be that catalytic log space can do all of P, which would be actually quite remarkable, but I don't know. So in order to study a little bit better the class of catalytic log space, we looked at the non-deterministic variant of this thing, and it is, as you expect, actually there's a couple of flavors that you can explore. It is a non-deterministic Turing machine, so it has non-deterministic moves, and we require that at the end of the day, no matter what non-deterministic moves you made, you have to revert back the catalytic space. So for any choice, it has to come back. But of course, the catalytic space itself may have a different behavior on how your computation goes and which non-deterministic moves you take. And again, we focus on logarithmic bits of free space and polynomial bits of auxiliary space. And we look at this non-deterministic variant. And we ask the question, is this more powerful than deterministic catalytic space? And we don't know, but we can still show that non-deterministic catalytic space is still contained in ZPP. So it doesn't boost you outside of ZPP. And then we try to play all the tricks that we know exist for non-deterministic log space, and we try to prove it's close to the complementation. And we succeeded, but we really needed to work hard here, and we needed actually as an assumption that pseudo-random number generators of a certain type exist. And the problem all the time is that these catalytic space machines can have exponential number of possibilities that they can explore on certain input settings, on certain catalytic tape settings. We also showed that there is a hierarchy for catalytic space, so these things behave nicely, and the picture is as follows now, that catalytic non-deterministic log space equals the complement, and it sits in between catalytic space and ZPP. So then, moving to the end of my talk, we had another idea. Actually, this is also an idea that comes to mind when you play around with this thing, and that's the following. Suppose that either I use my auxiliary tape, if it's incompressible, then I use it as good random bits. And if it's not incompressible, hence it's compressible, I compress it and I have freed up some extra space, which I can then use to do something more. And if lucky, these two are really complementary. Right? If one doesn't hold, I can actually compress. And so this actually almost worked. So we went back to an old paper of Nissan that was studying the following question for log space. And this one here indicates that, so you have an extra tape which contains random bits, and the one indicates that you can only read each bit once. So you cannot pass over it twice. And what Noam showed was that if you have this read once log space machine with two-sided bounded error, then actually that's contained in zero error log space. But now this machine may have several passes over the random bits. And sort of a main ingredient in Nissan's construction is the following notion. So he defines the set L of V of I that contains all the strings X that if you use them as bit flips, they end in V, and V is one of the configurations after you've used I of these flips, right? So it's a read once over the X's, so this I is well defined. And then he looks at the set of strings LVI of 0, that's the set that sits here, and that continue with a 0. And likewise, he looks at the set of strings that continue with a 1 in the I plus first position. So he uses this notion, and then he also says a set is epsilon good. So it's epsilon good set of random strings, or sort of a set of pseudo-random strings if the following holds. If LV intersect S 1 minus LV intersect 0 with S, that difference, the absolute value, is not much smaller than some epsilon times S. In particular, what this says is that the number of ways my random string continue with a 0 is about the same as the way it continues with a 1. And what Nissan shows is that if you pick randomly a set S of polynomial size, then it's good in this sense. And moreover, you can actually also check this goodness in L. Right? You can check that this requirement is satisfied in log space. And he also showed that if you have a good set, then it can actually be used to de-randomize your log space computation. So this particular log space computation. And then, of course, this ZPP algorithm goes as follows. You flip a random set S, you check that it's good. If it's not good, you stop. You say, I don't know. And if it is good, which you can check in log space, you continue. And so you will never make a mistake, but you still need your randomness. So this is what we use. And we use exactly the same ideas. So we use our sets, it's the same setup, but we observe the following, that if we set our auxiliary tape to be this set of coin flips S, then either we can, in log space, check whether this is a good set, and if it is, then we use it to de-randomize, but also, because of this nice nature of checking, if it isn't true, that means that this difference is larger than some fraction of S. That means that at a certain point in our set S, there's many more zeros than ones, or many more ones than zeros, one way or the other, which means that we can compress it. And so we have a nice way of in place compressing this part and uncompressing it later. And then we can use the freed up space to do a brute force de-randomization of our machine. So it shows that sort of the one pass bounded error version of catalytic space is contained in catalytic space. However, doesn't quite work exactly, because all of this stuff works only well when our configuration graph is not too big. And as we've seen, it can be actually very big. And when it is, then this sort of breaks down. So this is somehow work in progress, but somehow it's nice that you can get something out of this.
When you do the determinant result, does the configuration graph get big?
No.
So you don't have any examples where the configuration graph is?
Well, actually, this simulation here is an example where it does, because we compress and then we use the freed up space to do something useful with it. Yeah. But and the stupid example I had in the beginning, where if your tape happens to be all zeros, you just do something stupid for a long time.
Yeah, I just wondered if there was an example where you could do something new, where you required it.
I don't think so, and I mean, you would have to sort of make that intuition precise. I agree. I completely understand what you're saying, and you need to make that precise. That you can only do stupid things with this extra tape. It's sort of, what does this catalytic thing mean? There's a couple of ways you can interpret this thing. So one way is going that, so we showed that you can do NL with this catalytic space. And so what does that mean? So here's one application of Hartmut-Klauk that may be actually quite useful in the future. So you can start your catalytic simulation of your transparent program, and you start your additional tape with completely random bits. And now at every step of the catalytic computation, you can show that the contents of the catalytic tape remain random if you don't know what is in this clean space part. So, but given two snapshots, actually, you can figure out, you get some information from the two differences in tapes. But if you get one snapshot, you don't know anything. And so what you could do is that when you're doing some computation that's forbidden, and somebody wants your computer, you just download quickly the small clean space on your USB stick and take it with you and erase that. And then the remaining space is completely random and contains no information whatsoever about what you were doing. So another application is due to Ken Regan, who reviewed this paper, and they had the idea that this could be fantastic malware, right? Because you can implant some virus in your computer, and it is using the memory that is there to do something nasty, but you're not noticing it, because at the end of it being nasty, it sets back your memory the way it was. So you can do something which they dubbed stealth computation. And the third application is that of Peter Sack in cryptography, where he says, well, it was actually, they have this notion called a proof of space and proof of secure erasure. And it was believed that these two were the same. But actually, it is not true, because our result somehow sheds some doubt on these assumptions here, because you can actually use your space without erasing it and setting it back, right? So you can somehow give a proof of space without you really doing it. So, concluding, my conclusion is at least that full memory helps. And here is my full memory that I have of Mike and Eric. And I want to and by congratulating them. And hopefully we will have many, many more nice and happy memories that we can celebrate indeed in 60 years from now. And I have a small present, but yeah. Yes.
What is it?
Memory.
Yeah.
Don't open it.
What do you believe? Is it does it contain P or not?
I don't think it contains all of P, but I mean, there is some hope that you can go a little bit beyond the results that we have now. There's no reason to believe it should stop there.
You think it's somewhere in NC?
Yeah, so the next thing that you could try is NC2 to see if you can compute that.
Is there a sense in which it's a hardest to de-randomize problem in ZPP? Is there some sort of dependency like that now? Yeah,
It's a good, I don't know.
because it involves random strings. Seems like it should be.
But that would be another one, right? Try to de-randomize this one as opposed to de-randomize all of ZPP, just focus on this one. But, yeah, we tried, but I have no conclusive answer there. It might also be, Avi, the case that actually this is another possibility that this catalytic space, because your intuition tells you it's useless, right, to have something additional there, that it is indeed useless and that TC1 and non-deterministic log space is equal to log space. And this would be the way to show it.
So this isn't likely to, or it doesn't obviously have complete sets, right?
No, because it has this sort of a semantic definition.
So, I mean, there's also this possibility that it's just some weird class that doesn't really correspond to nice subclass P.
Yeah.
Just happens to contain some nice subclasses.
Yeah. So it's a beast in its own right. Yeah.
So the pseudo-random generator used to show closeness and
Yes.
Do they randomize it?
No, I don't think so. There are space de-randomization pseudo-random generators.
Operations other than the plus, minus, and these times that you address here, like if you addressed harder functions or harder operations?
Well, I mean, we use the well, these are the plus and the times in the ring that we use, and so you can use more complex rings. We haven't explored any other operations than that. But I guess, I mean, as long as you can compute it in log space, you can do it, right? The whole transparent translation will go through.